Okay, welcome everyone. So today we're continuing our mini series on self-supervised learning. We're really excited to have a guest speaker in class today, Michael Auli. Michael is a research scientist director at Facebook AI Research, and he's done a lot of interesting work over the years. Neural dialogue models from early on, neural machine translation, to most recently some of the unsupervised speech and language work. And he's been pursuing this agenda on self-supervised learning that we're really excited to hear about. So this nicely complements the lecture by Ishan last week, which focused on self-supervised learning for vision. And today we'll hear self-supervised learning in a different domain, which is speech processing. So over to you, Michael.
Thank you for the very nice introduction. So as Drew already gave away, I'll be talking about speech, and here's a list of all the people I've worked with over the years on speech, without whom this work would have not been possible. So speech technology is actually very useful, and actually now pretty prevalent as well. If you look around in our daily lives, right? We might see video captions on, for example, YouTube or other video streaming services, and many of them are actually automatic, particularly on YouTube. Then we increasingly use our mobile devices using speech in a very convenient way. You don't have to type and so on anymore. That can be very convenient. And then we also have like home devices with which we can interact, for example, like Alexa, like the Amazon devices, Google, and so on. And while we might see this as something that is a convenient way to interact with technology, it certainly is for people who have access to good access to education. For the vast majority of, or for many people in the world, speech may be pretty much the only way to be able to interact with technology and to access information. So what kind of speech applications are there, right? So from an academic point of view, we distinguish between the task of recognizing speech. So for example, we might dictate something to our mobile phone, and that speech recognition model then just turns it into a string of text. Then there's the converse task of taking some text and turning it, synthesizing it into speech. So there's a lot of apps that just read out things aloud, or maybe your personal assistant responding to you directly in speech that requires synthesizing text. Then there is something that's known as keyword spotting. So for example, just spotting that you say the name of your favorite home device. Another task is to verify that it's really you that's speaking or some other person, which is known as speaker identification. And then there's sort of broader tasks like just identifying the language that somebody is speaking. So you may consider, like, if you run a production system in speech where you can recognize many different languages, you want to first know which language is actually spoken before you try to send that audio recording to your production system in a particular language, because otherwise it will just not work. And then there's another interesting task which is known as speech translation. So we translate some audio, some speech recording directly into another language, and then might also synthesize it into speech again. So you have that speech-to-speech translation. You basically have an interpreter, a machine interpreter. So what I'll be talking about today is a little bit about just how traditional speech recognition is done, and then talk about self-supervised learning for speech. And I'll talk about the algorithm we developed, the latest algorithm, Wave2Back 2.0. Then I'll talk about generalizing it to different languages, so we can build self-supervised representations for multiple languages at the same time. And then I'll talk about how we can do speech recognition without any supervision at all, and why that might be useful. So traditional speech recognition is simply given some speech audio recording, turn it into a string of text. And the way that is done is that speech audio recording here at the bottom, this raw waveform, is turned into a feature representation. So there's some feature extraction happening, and I'll talk about it in a second. And then once you have these features F, well, we want to arrive at a transcription, basically a string of text, which is denoted here as W. And the way traditional models go about this is they do it in a reverse way. And by that I mean is they estimate an acoustic model that basically gives you the probability of that feature representation F given a suitable transcription. So typically when you have a direct model, you would get a transcription. You would get the probability of a transcription given the feature input. This is the other way around, so it employs the base rule, right? And then there's also a language model that gives us an idea of how fluent a given transcription is. And that language model is just estimated on completely unlabeled text from your favorite source. Let's say Common Crawl, some of the internet, etc., depending on the application. But the crucial point is you have this kind of reverse model that basically estimates the probability of the feature given some transcription you have to find.
And Michael?
Yes.
A quick question here. For people who don't work in the speech literature, I imagine that there are some benefits of approaching this through Bayes' rule and through the reverse direction, that the language model can rely on non-speech data. You can just get data from the web to build a language model, which I guess is one of the strengths of this approach.
Yes. So yeah, that's a very crucial point here. Yes, and that idea of having this kind of reverse approach is not just something people do in speech; they also do it in machine translation, or used to do it, right? I'm talking about like pre-neural nets, pre-2012. So that idea is very prevalent in basically text and speech processing. It's probably one of the most important ideas of these models.
Sounds good. Yeah. Thank you.
So going a little bit into more detail of how this traditional pipeline works is, so these transcriptions, W, they are usually not just represented as a string of words, but as more fine-grained units, as so-called phonemes that, in some level are just distinct units of sound, distinct units of sound just to distinguish words, right? So it's basically like a way to denote a word and how it sounds, and that is the idea here is that this is just easier to recognize, because sometimes we do have words that in written form they are not every graphemic unit or everything in a word is necessarily pronounced in a very, very clear way, in a very high level. So with this idea in mind, this traditional pipeline is complicated a little bit more even. So instead of basically going from feature representations to words, what we do first is we actually come up with a sequence of these phonemes, Q, with the acoustic model to explain the feature representation input. And then we basically try to figure out a transcription to give us that gives us a good probability of this phoneme sequence. So we have this two-step approach here, and because there's many different ways we can potentially pronounce a word, is we do sum over that. So on the left at the bottom equation, you see a sum here over those for the pronunciation model. So that's pretty much what I will be talking about traditional speech recognition models. But because this talk is titled around self-supervised representation learning, I'll be talking mostly about feature representations here at the bottom, and how we can learn those from unlabeled data. But let's look at how these feature representations in traditional models look like. So we typically have like an audio recording that has a sampling rate, 8 or 16 kilohertz, or even more these days. And then what people do is they build these feature representations, they build spectrograms. And what is a spectrogram? Well, basically you take a very small window of this recording in the raw waveform, and you compute just a fast Fourier transform, and you look at the magnitude of that. And what you get is, for this very small window, is you get basically like an idea of how frequent certain like what the frequency domain looks like there in terms of the recording. And then you get a frame that describes this 20 millisecond window, and you stitch all those frames together to get your spectrogram. This is pretty much what is being fed into traditional speech recognition models, and based on that, they then try to come up with a transcription. And people came up with this through lots of trial and error. Basically, this is like what people came up with, like with doing lots of feature engineering. Oh, I think this is my slides, right? Yes.
Yeah, they're back.
Good. Sorry about that. So that's pretty much what I will talk about, like how traditional speech recognition works. That's a very rough overview. And now I'll talk a little bit about how we can learn good features from completely unlabeled data, how we can basically learn the structure of speech, having no labels, and then do very, very efficient learning based on that. And I'll go into more detail there and all of those things. So typically how we train speech recognition models in these traditional ways, that we collect thousands of hours sometimes of transcribed data for good systems. And what I mean by collecting is we basically give people speech recordings and they write down the transcription, right? So there's lots of annotators who do that, and they do that for a particular language, for a particular dialect, most likely, and for a particular domain, right? To give you some idea, in English, a very popular domain is audiobooks. Okay? So it's read speech, English, by most likely a very certain demographic in the United States, which reads those audiobooks. So important detail there is also like people might also just read a book and then get the recording this way. So you can go both ways to get the data. But the important point is this process requires a lot of data to train models in this traditional way. And it is very specific to a particular language, dialect, and domain. And this brings us to the shortcoming of supervised learning, which is that you collect data for a particular narrow domain and so on. And when you then present at a test time with a completely different setup, for example, you might collect pictures of cats, right, at the top here, and then at test time you get a slightly different picture of a cat, then your model may just not work. And the downside is also of supervised learning that you have to obviously collect all of this data, right? And aside from this, presenting your model with input and output examples, and this is the sole way it learns. That's not how human beings learn either, right? Human beings learn a lot through just basically observing what's going on around the world, listening to sounds, looking at things, and then building their own mental model of how things work without explicit supervision. People don't learn to speak by just being presented with by being presented with exact supervision of how to do things. They try things out and get an idea of how it works, and then learn a little bit from explicit instruction. So
Michael,
the entire idea, yes.
So a couple of questions have come in that I think I can ask you here. So one question is, how do we verify human annotated data sets for speech or for other tasks in general? So does a secondary annotation process happen where someone goes in and checks the quality, or is there an automated way of checking consistency, or how are these things done?
Well, it really depends on the data set, right? There's different protocols, right? There's, for example, the Mozilla Common Voice project. So that's just a data set you can download of read speech as well. And there are typically people being asked to read out, I think some text from Wikipedia it is mostly. And then a second person verifies that this is actually the person read that particular text, right? So there's this verification step as well, right? And then, so oftentimes there is such a step. People are much more rigorous for test data than training data, right? So for test data, there's much more verification. There might be like multiple people actually like, really having to vet, hey, this is a good quality sample. The speech recording really is properly reading this very clearly, or and so on, right? Just so we can actually measure progress well, versus for training data, there's usually less so.
Got it.
Yeah.
Got it. And the next question is in I guess modern deep learning. So the question is about how do we measure how good a feature or a feature transform is? And I guess the context for this question is in deep or like end-to-end trained architectures. We know how good a feature representation is by just checking final accuracy because it's one large system, right? How are these things? How are these things done in the classical pipelines? So someone chose, the MFCC or some frequency-based representation. Did they just look at the downstream accuracy to tell if it was a good transform, or were they looking at something else?
I think that's an excellent question. So I think at the end of the day, what matters is really like at the end of the day, the downstream accuracy is what people pay mostly attention to in the speech community. But what has emerged also is that particularly in the context of self-supervised learning, which we'll be talking about next, that people they learn these representations and then they would like to understand if they are really able to distinguish between certain types of sounds, right? Mm-hmm. So there's this zero speech challenge that's organized by our own Emmanuel Dupont at FAIR, and there like one test is really to see if two representations, so basically two sounds in the same sound in two different words, right? You get hold on. What you do is you get representations for two words which contain the same sound, and you want those representations to be similar than a word that doesn't contain that sound, right? So there's that sort of direct evaluation there as well, right? But so that doesn't require you to actually collect like a downstream accuracy, which is obviously much more work than do this direct evaluation.
Got it. Thank you. Please continue.
Okay, so shortcomings of supervised learning, there are quite a few. So the goal of self-supervised learning is to learn good representations of audio data from audio that doesn't have any transcriptions, no labels whatsoever. And that's what I will be talking about next. But then the question is, what can we do with these representations? And we can actually do a lot. We can solve pretty much all of these speech tasks. So in a very simplified way, if we have a pre-trained model that gives us, or a self-supervised model that gives us a representation of audio, which I denote here as like a little vector with numbers, then we can just stick a classifier on top that then transcribes this audio into text. And that's what we actually do in practice. And that's how we solve speech recognition. We may also then, instead of just transcribing this English audio into English, we might also just directly translate it into a foreign language, speech translation. And that also works remarkably well. And we can also solve other tasks, like, for example, detecting if this is actually speech, or if it's music, or if it's noise, etc., etc. So once we have such representations, then we can do a lot of things. Now the question is, how do we get those representations? So how does this blue box work? Well, one proposal that we worked on in our team over the years is an approach called wave to back. And let me go into the gory details of how that works. Well, it's a model that works very similarly to BERT, but how does it work in practice? You get you get some speech audio, so the raw waveform encoding, and then what we do is we just run a convolutional neural net over it to get feature representations, and we call them these latent speech representations D. And then what we do is we feed that into a transformer network that basically, I think there will be a future lecture about that, but basically what it does is it just gives us high-level representations that contextualize these representations. So basically encodes the entire sequence, but centered around a particular time step in your convolutional neural network. You can just think about it as like a more powerful convolutional neural network. And then we get these context representations D. And then you basically have representations for the entire audio sequence. And then the self-supervised learning starts. So the self-supervised learning is simply, we just take some of these latent speech representations, on average actually half of them, and we just blank them out. So we just make holes in our data representations for the learning task. So we remove some of that, and then we ask our model at the top to basically predict what's behind that feature representation. So which one, what does the representation look like? And that's known as like mask prediction. And that's sort of the task that we try to basically unmask some of the time steps that we mask. But the question is, what do we want to predict? So I said these latent speech representations, C, well, they are just vectors again, right? So are we just going to reconstruct these vectors? We tried that, but what works better is that if we actually learn an inventory of speech units. So I talked initially about phonemes, right? So there's a phoneme set that that covers pretty much a lot of the human sounds that we have. So we want to learn something similar, and we do that by basically taking these latent speech representations and we quantize them. So basically what that means is we just try to assign each one of those CNN outputs to a fixed inventory of possible representations. You can think about it as learning a vocabulary of speech sounds. That's what happens there. And once we did that, then we just basically get a fixed vocabulary unit. I call it here Q for each one of those CNN outputs. And then what the network at the top does, the context representation network, it just tries to predict for the masked time steps which one is the right quantized one for the hidden ones, for the ones that are masked. And zooming out, what is happening here is you can think about this task as like doing joint vector quantization of the input data, as well as learning a context representation, which is what happens above the CNN. And what we do is, in practice, we contrast the true quantized with some distractors that we sample.
Michael?
Yes.
I have a question and a comment. So I guess one comment for the students is, the mask prediction that Michael's talking about here is conceptually very similar to what Ishan was talking about in patch prediction of images. So that's a connection that I want to make for the students. And a question for you, Michael, is on this slide, can you comment on why you're using a CNN at the first layer as opposed to like an RNN or an LSTM or a bidirectional RNN/LSTM? I presume these things have been tried and CNNs work better, but could you comment on why?
Yeah, so I think so there was actually some prior work that I didn't mention here, and they used some of these more fancy architectures that you mentioned, like RNNs and so on. But when we got into this line of work a few years ago, we didn't know about a lot about speech, and people don't know a lot about speech, but I'm learning. Is that we just try to use simpler architectures. So CNN can be very well understood. It has like a fixed receptive window. There's a fixed stride. Everything is simple. It has both pros and cons. And what we found is that the CNN worked as well as using an RNN for this particular task. The nice thing about the CNN is you can parallelize it. Like it works very efficiently on GPUs. I mean, RNNs, of course, as well. But for the CNN, you can compute the entire CNN for the entire layer, simultaneously. And the nice thing about the CNN is we can exactly control how much information is encoded for a particular blue rectangle blue square rather here, like, how much information is in one of those latent speech representations. So we can completely control that. And that suits us really well for when we want to then set up this mask prediction task, right? Because if this triangle at the bottom, if there's no borders defined, an RNN can take information from somewhere else and move it in there and so on, right? With the CNN, that's not possible. So we can very well control the learning task here. So it's both simple, and it suits us very well for this kind of mask prediction task, because we can control exactly what's behind one of those quantized units.
Got it. There's a second question that's somewhat unrelated to this slide, but more related to the larger topic here, which is, can you comment on, so most of these data sets, as you mentioned, are sometimes disproportionately focused on English-speaking countries and maybe have overrepresentation of certain dialects. Can you comment on whether self-supervised learning techniques fall prey to the same kinds of biased representations that supervised learning techniques might fall prey to? Or how is generally bias avoided in these kinds of methods?
I think first of all, I think it will be very hard to avoid it entirely, but kind of approach, I will be talking about that a little bit later, but just as a quick preview, what we have been trying to do is to say, okay, labeled data is really, really hard to get, right? But getting unlabeled data is a lot easier. Getting unlabeled data for a more diverse, getting more diverse speech data is much easier if you don't have to label it, right?
Yep.
And so our approach, or one thing that might help you a little bit, it's definitely not the full answer, is to say, hey, let's just get these general speech representations, let's make them as diverse as possible, and then let's use some labeled data to actually, like, to basically solve some task. And we did find that even though this labeled data is very biased, you do find that you get better performance on data that is out of domain, right? For example, right? That is not like this labeled data, right? Just because the original representations they were learned on a more diverse set.
Got it.
That might partially help.
Yeah. And I guess final question on this slide, even though this slide only shows one gray box as the mask, in practice, you're masking multiple of them, right? There's a certain, maybe something like...
Yeah. I will talk about it in a second, but we mask about half of them, really, because it's actually, the model is really, really, really good in identifying those boxes, because the speech signal is very correlated, right? When I say something, it's very easy for you to predict, like, the next 120, 200 milliseconds, even further ahead, right? It's really easy to do. You have to make it hard for all to learn something. But let me get into that in a second.
Please continue.
So just digging a little bit into this loss, right? And that's how we train this model. So I said we have this contrastive loss, and maybe Ishan mentioned it as well. We just used a very simple loss that basically softmax loss here. What we do is we compute here a cosine similarity. So in the numerator and the denominator, there's cosine similarities between this context representation C for a particular time step T and one of those Qs, and the true Q, sorry, not just any one. At the numerator, you have the true quantized representation, which is the representation of this particular sound, and you compute the similarity between that. And then on the denominator, we just sample lots of distractors from the same sequence, but also from other sequences, and compute those similarities, and we just contrast those things. And what we want is we want the numerator to be obviously very large and the denominator very small. And then we also have like a temperature and so on, very similar to what people do in computer vision. So that's how the loss here works. Now, in terms of how many things we want to mask, as I mentioned already earlier, we do mask a lot. And the way we go about it is we don't just mask individual time steps, because these time steps are really short. They're 20 milliseconds. And predicting what's going on in the next 20 milliseconds, that is super easy if you're the previous one. So we mask entire spans. We mask typically 10 time steps. So that is on the order of 200 milliseconds. But what happens in practice is, because we have many of these spans, they do overlap. And then for typical training example, in our favorite, like in our main benchmark, where samples are about 50 seconds long, half of the time steps are masked, and the average span length is about 300 milliseconds. And that gives like a good, decent task that is not too difficult, but also not too easy, because if it's too easy, then your model doesn't learn anything. So once this model is trained, actually, any questions at this point before I move on?
No, I'm not seeing any other question coming about this slide.
Let me pause in a second again, and then other questions. So once this model is trained, then we can come back to this illustration that I had before, like, where we stick classifiers on top to solve certain tasks, and we really just take that model and then just put a linear layer on top that just maps into our vocabulary of characters. That's what we do in speech recognition. We just map to characters, and then just train it with a standard loss in speech recognition to basically fine tune it on the label data. What that means is we just have a bunch of label data, actually very little, as I will talk about in a second, and then we just train this entire model to perform the task of speech recognition or any other task. We also do a little bit of regularization, by basically masking out some parts of these latent representations. Technique is called spec augment in speech recognition, but basically what we do is we just mask some of the channels to regularize a little bit there, and then we use a language model, like mentioned initially, that helps us to identify fluent output. So how does this work compared to the state of the art? So we looked at like a bunch of setups here. So this is the Libri speech setup, and that's a very, very saturated benchmark, because you can see the word error rates, they're like in the low single digits, right? And this is a benchmark where people just took audiobooks and then read them out, and then they have the text and they have the speech recordings, and this is what we train our models on. And there's about 1,000 hours of this data. And people managed to reduce the word error rate here a lot. What we can see is the previous state of the art here, which is a purely supervised model in gray. And then there is this, at the time, that was like the really best model here that used another 60,000 hours of unlabeled data to do self-training. I'll discuss that in a second. And the blue bar is like the approach that I just described. So it does pretty much as well. And that's really the first time, or that was last year the first time, that these self-supervised approaches have been shown to be as good as the very best models that are out there. But people have engineered a lot. In speech recognition, people really engineer a lot. And our pipeline is actually relatively simple. But what's
Michael?
Yes.
Sorry to interrupt. One question for someone who may not be working in the area of speech recognition. So a word error rate of 3 or 4.5, I know you mentioned that the data set is getting saturated, but is that considered good enough for production? Like how should someone who doesn't work in this area treat this number?
Yeah, so I think, so this is a very, very low number, right? But to answer the question, is this good enough for production? Well, it depends what your production is. Most likely your production setup is not people reading audiobooks, right? It is like people being somewhere in a noisy street talking to their phone, right? And then these models would do a lot worse, right? But we don't have very good benchmarks for these settings yet. People are working on that, right? But in terms of, so I mean, to answer that question in a simple way, if you're getting in that regime, then you probably have a model that will also do well in these kind of noisy settings, right? But that needs to be confirmed. But this is like the sort of these are the numbers that you get like on these very well studied like public benchmarks that we have. But it is TBD if that will translate to good performance in a more noisy setting, where most likely the error rates will be much higher, just because it's much harder.
Yep, got it. Thank you.
So this is when you have a lot of labeled data, but I talked about initially about like, all the languages of the world. We have about 7,000 different languages according to linguists, many more dialects, and then also different domains. What can you do with a lot less labeled data? Because you just can't collect 1,000 hours for every one of those settings. It's just not possible. Well, this is where it gets really interesting, and this is where self-supervised learning really shines. So what I'm showing here is the same, like, state-of-the-art approach in red here, when trained with 100 hours of labeled data. And they also use the remaining 860 hours for their semi-supervised training. I'll describe it in a second. But when we use the self-supervised approach that I mentioned here in blue again, then it does a lot better if you train it with the same amount of labeled data. So this is quite a significant difference here, going from 8.6 to 5. But then when we use even less labeled data, let's say an hour in orange here, then you're still doing slightly better. And when you use just 10 minutes, then yes, of course you're worse, but it's not a whole lot. 10 minutes is definitely a lot less than 100 hours. And then the very last bar shows that if you would use more unlabeled data for the pre-training approach, then you can get back to actually slightly below that approach that got like 100 hours. So this is the very exciting result about that work, that you can be very sample efficient from a labeled data perspective, and that enables to do speech processing for a lot more languages and domains at a decent quality with less labeled data. So self-supervised learning that can be effective for both high and low resource, particularly for low resource. And what we found also interesting was that looking here at the effect of model size and amount of unlabeled data for different labeled data regimes on the x-axis. So here we train like a model with 100 million parameters, and obviously as you increase the amount of labeled data, performance gets better, no surprise. But if you just increase the model size, triple number of parameters, then you also get an improvement, which is quite a sizable improvement there on this benchmark, keeping everything else equal. And if you increase the amount of unlabeled data, then you get another nice big boost, which is very nice. In terms of how does this look like in practice, so how do some of these transcriptions look like with just 10 minutes of labeled data? And that's really not a lot, so kind of like our expectations here. But to give you an idea, 10 minutes of labeled data, that's basically like less than 30. That's really just like a handful of utterances. I think it's like 24 of 24 sentences that people speak. It's very little data. And what you can see here is the output hypothesis, that's the model output with no language model. You can see the spelling is very phonetic. Then the language model improves that quite a bit. And then at the bottom here, you have the reference for these two examples. So it's by far not perfect, but it is fairly readable actually, even there's so little training there. Any questions at this point?
Michael, one question. So in the second example, the output, for example, the embraid word and the quiet word, as you mentioned, those aren't actually in the vocabulary words, right? So, but you can still output them because phonemes have been stitched together, and it's pre-language model. That's kind of why we're looking at that output.
Yeah, sorry, it's actually characters. The model outputs characters, so you can spell anything, right? Yeah, and then with the language model, then the vocabulary is applied. So there's a fixed, so the language model requires every output to be a particular word, and then things change. Yeah.
Got it. There are a couple of questions that have come in. So what components of speech, that is pitch or speaker identity, are not embedded in this type of a model? Like, we're not modeling certain aspects, and could you comment what we're not modeling?
I think that's a very good question. we personally haven't looked that much into like really analyzing all of these representations at such a level. People are starting to do this, similar to how people have analyzed BERT in many different ways. So this field is called BERTology, and we see already papers doing the same thing for our model here, although I'm struggling to keep up on that front a little bit. But what definitely is possible that people can very quickly adapt those models to particular things like identifying speakers. So you take this model that is publicly available, and I'm going to talk about that in the next slide, and you can very quickly, with very little data, adapt it to solve a particular task, such as like identifying a speaker. Of course, with a little bit of labeled data, but that is possible. But these representations, they definitely encode some of that. I don't want to make any strong claims about how much, because we haven't really looked into that, but they definitely do encode some of that structure that is in speech.
Got it. And one other question that has come in: has there been work on mixing self-supervised learning with what used to be called semi-supervised learning, where you have access some labeled, some unlabeled data?
Yes. We've done some of that. I think in 2-3 slides I'll talk about that. And Google has done a lot of that as well to get the very best numbers on this benchmark. That is good.
Got it. We'll wait for that then. Please continue.
Cool. So if you're interested in getting into this area, actually our models are available on our own repository FairSeek on GitHub, but also Hugging Face made them available. And this is like a popular zoo of NLP models, and now they're adding speech models as well. And people, it's actually very easy to use, clearly, because they organized a little event, I think it was like a hackathon, where people took our models and fine-tuned them onto 73 different languages, with some nice results in many cases, actually. So if you're interested in using that, it's been made very easy to use. You go on the Hugging Face website and just look for Wave2Vec. Now on to the second question about combining self-supervised learning and semi-supervised learning, which is also known as one method that's known, the most popular one is known as self-training. And the idea there is that you have some labeled data and you have some unlabeled data, and you want to use that unlabeled data. And in self-training, what people do is they take the labeled data, estimate a supervised model in the standard way, and then they go to the unlabeled data, which are denoted as these little speech sequences, and use the supervised model to label it, to assign so-called pseudo labels. That's what it's called in the speech recognition literature. And then you suddenly have labeled examples as well, or more labeled examples. And then what people do is they just put everything together and then train a semi-supervised, or train a model that is obviously semi-supervised. And that works really well. And this is what I showed you earlier as this red bar, so the best system at the time. So that's what they did. And we compared our self-supervised learning to that, and they are performing roughly the same, at least in the high regime, in the high data regime. The low data regime, obviously the self-supervised one is much better. But then the question is, can you just combine these two things? And the answer is yes, and that's what we did. So what we did is we basically follow the same exact protocol, but this supervised model at the top, there is, in order to get that, we just do self-supervised learning and then fine-tune that model on the labeled data. And this is what then becomes the supervised model in this diagram here. And then you can use that fine-tuned Wave2Vec model to label your unlabeled examples. Again, the same unlabeled examples that we actually did pre-training or self-supervised learning on. And then you can get that model at the bottom. And this works really well, and we did that. And if you just look at this graph on the very right and you compare the last two bars, you can see that combining the two approaches, which is the last bar, works a lot better than just doing pre-training. And that's some work we did a year ago, and that was very nice to see that with just 10 minutes of label data, you can do as well as like systems that were trained about 2 years earlier with 960 hours of label data. And these were sort of the best systems at the time. Yeah. So that can be very effective. Very good. Any questions at this point before I move on to the next quick topic?
We actually have one question that came in about earlier slide. Can you comment a bit about how once a character level output is present and a language model is inserted, how the language model incorporates word tokens or predictions at word level from the character level predictions? Is it through some similarity score or something else?
Yeah. So have you covered beam search in your
We have covered,
lectures?
yes, we have covered beam search.
Yeah. So basically, what happens is it's a beam search. What you do is you can think about the acoustic model, which is our wave-to-vec model here. That model can output anything, right? It has like a character vocabulary, and it can generate any kind of word or non-word, right? And what happens in the beam search is that you try to figure out what is the most likely output according to your acoustic model, as well as the language model. Now, the language model is a lot more opinionated than it's a lot more constrained because it will only allow valid, fluent string sequences or transcriptions. And so what you do is you score each possible path. Like if you think about like vocabulary having like 30 units and then, having a certain number of time steps, it becomes very exponential. You look at each one of them, and then the acoustic model has a score for a particular path, and then your language model. And if you combine these two, then what will happen is that sequences that are both very likely according to the acoustic model and the language model will survive in the beam search, because in beam search you prune as you go along.
Got it. Perfect. Thank you. Those were all the questions at this point.
Cool. Okay, so then let me get back to the topic about like many different languages and dialects, etc., because right now I just talked about English work and that's fine. But where this gets really interesting is in settings where you just don't have these thousands of hours of data, which is the case for the vast majority of languages in the world. And one approach that we looked into there is crosslingual training, right? Because and what that is we train models that can understand speech in many different languages. And the idea is what happens in practice is that in settings where you have little labeled data, so let's say you have some foreign language, you have little labeled data. Often you have little unlabeled data as well. It's not so that is also a problem. If you have little data, it's not just labeled data. And the idea of crosslingual training is that you train a single model on many languages, which have either low or a lot of unlabeled data or little unlabeled data. And what we want to happen is that the data that we have from languages that have a lot of data, that will hopefully help the languages which have little data. We want to improve the performance on languages that just have little data or low resource language. And the idea is also that then you have just a single model, right, for all your languages. So instead of having like a separate model for all your nearly 7,000 languages in the world and every domain, that's just not feasible, right? So this is sort of a first step towards going like having a single model that can understand speech in many different languages, domains, etc. And the way we went about this is a very straightforward way. We just basically took the training data for lots of different languages and just trained the same model that I described earlier, doing nothing special. And the Venn diagram you can see at the right here is just simply illustrating what happens in practices, right? Because remember, in this wave-to-vec training, we identify speech units, right? But what we found in practice is that speech units are then being shared across different languages. So we have basically training data that is a mix of different languages here, English, Chinese, French, and then many more languages. And what we find is that some of these units, they're being shared across different languages, which is actually very interesting. Just simply because languages do share sounds. And I'll show an analysis about that in more detail later. But back to the cross-lingual aspect, we ran an experiment there where we try to understand if there is this kind of transfer of basically some like the high resource languages benefiting low resource languages. And the experiment we ran is we just pre-trained the wave-to-back model on 10 different languages, and then we compared that to just training models on each language individually. This is what the first set of bars shows. First set is in green here, the performance if I train a separate wave-to-back model, or we call it XLSR model in that case, for each one of those 10 languages. Then some of them are high resource and they perform pretty well. And some of them are low resource and they perform, well, not so well. As you can see, they have a very high error rate. But then if you train such a model all together, so like all the languages, a single model, then the performance for the low resource languages is vastly improved. But problem is, the high resource languages got a little bit worse, right? This is the middle set of bars. And then on the right, you can see what we did about that. And the simple solution that we found is to just increase the model size. So we just tripled the model size. We trained a large transform model that is just 3 times as big as the original one. And then the performance on the high resource languages, was nearly as good as if you train individual languages. And the reason why a larger model helps is because suddenly you task the model to understand 10 different languages instead of 1. You need a bigger model to do the job, simply. Yeah.
Michael,
Yes.
There's a question that came in. How many speech units do you typically find for each language? And does this align with the number of phonemes in that language?
So we don't really, we don't do anything. We don't tell the model how many units it can allocate per language, because in this experiment we have 10, right? What we do is we have 2 code books that we have a code book that is of size of 320 different units. That's what we have. Yeah.
And in computer vision, there have been some papers where people have gone in, looked at activations of various neurons in a CNN, or and tried to post hoc give them names as to what kinds of patterns that they may be detecting in images. Do you know if any such work has happened in speech where we post hoc look at the trained networks and try to make the representations or the activations or neurons or units and give them semantic names?
Yeah, I think so. We did try to do a little bit of that ourselves. So we tried to correlate. Actually, I only answered half of the question before, but it's actually related to this. So what we tried to do is we tried to understand how we try to understand which one of those codebook entries or which one of those units co-occurs with phonemes, right? And what we find is that there is a strong correlation, but it's not a one-to-one correlation. What we do find is that we have 320 different units, right? But obviously there's not as many. I mean, there's not as many phonemes, at least in English, right? There's a lot less. I think it's less than 50 even. And so what we find is that multiple of our codebook entries or our own units correspond to some of those phonemes, right? Just because we don't constrain the model in any way, it just makes use of that model capacity in whichever way it sees fit. Yeah, but that I think there's a graph if you look at our paper, it's in the appendix, where we sort of show that some of these units correspond to some of these phonemes.
There's no other question at this point, so we can continue.
Cool. Then the last point that we also did is now that we have this single model, right? So far we just fine-tuned this model for each language individually, but obviously we can also just basically take the label data for all these 10 different languages and then just basically fine-tune the model on this data, and then you can recognize speech in 10 different languages. And what we found is that this works actually pretty much the same as if we would individually fine-tune for each language separately, which is what we call monolingual fine-tuning. So the exciting thing about that is that now we will be able to build speech recognition models that can recognize many different languages and can transcribe in many different languages. And then in terms of these quantized units, like how they are used across languages, we did a little analysis here. So this analysis is not perfect. People always find lots of corner cases here and so on. But what we basically did is we wanted to understand these units that we learned. How are they being used across languages? And we did a very, very crude experiment here. We just took the test set, the development set, sorry, for each one of those languages. And then we compute the quantized units that are used for all the speech sequences in these def sets. And we just write down how often a particular unit is used in Chinese, French, German, English, etc. And then we get these vectors basically that tell us how they're distributed. And we just do a little PCA over it, and this is what you get. Now, important point is these def sets, they are not for this. They are for different utterances. So people are not saying the same thing in Chinese or French and German, right? So there's this variation as well. And what you can see is that there is a clustering. Of course, it is not perfect, right? I mean, you'll easily find fault why one thing is closer to the other. But it's just interesting to see that there's some structure that falls out given no supervision whatsoever. We don't tell the model that this is Chinese or this is English or German. It just, it just figures out itself that English and German, they have more similar sounds than, let's say, some of the other languages that are further away. Okay, maybe I move on to the last part. Should be fairly quick, unless people have questions.
There's one more question that has come in. So can you comment on whether people have tried transfer learning from high resource languages to low resource languages, and does training a single model on multiple languages work better than that?
Training a single model on multiple. So the transfer learning, yes, people have done that previously in speech recognition. But one major limitation of that is that we only have so many high resource languages, and it's a baseline that we probably should have considered more in this work, but just setting up that high resource system in a credible way was difficult. But the point is, yes, so that's something that people have tried previously a lot pre self-supervised learning. But one downside with it is that there's not that many high resource languages. The only languages that are really well resourced is maybe there's maybe 10 or 15 languages in the world there's no more than 30 languages in the world where, speech recognition even works even close to what it does in English, right? And so you just don't have necessarily always a good high resource language that you can use to transfer to some kind of low resource language. Because we have a lot of languages that are just not related to often European languages, right? But yeah, this is a good baseline to consider and something we should probably do in the future. Yeah.
Thank you. Yeah, those are all the questions for now, so we can continue.
Cool. So now maybe the last part. So this is some of our latest work, and that's really around how do we learn to process speech without any supervision at all, right? So far I always talked about doing pre-training, self-supervised learning, and then doing some type of fine-tuning, and that's just another way to say we use a little bit of labeled data to actually adapt them all to solve a task. But I think what is very exciting from an AI perspective is, can we actually solve some of these tasks without any labeled data at all? Can we build machines that can learn without any supervision, and to just basically really through observation, right? And that opens the door to make this technology much more ubiquitous, because you just don't need to collect any labeled data. You just need a bunch of recordings, unlabeled data, and you train a self-supervised model, and then you can hopefully build a speech recognition model for some language for which no data exists. So the motivation is remove the need for labeled data entirely. The idea of doing unsupervised learning has been shown to work in other tasks like machine translation. where it works reasonably well for some languages. And the question is, can we do the same thing for speech? But the main difference between machine translation and speech is that in machine translation, somebody wrote down a sentence, and in many languages, not in all of them, we do have word boundaries. And we can make use of them to identify the units that we want to translate. Now, the problem in speech is, well, we have things like this depiction of a raw waveform, where the units are not so clear. So it's not entirely clear if there is a break, if that's really the end of the word or not, or the end of the phoneme or not. So this is a bit more tricky. So this brings us to the main challenge, how to learn the segmentation. But the key ideas that we're building on here is, well, we wanted to, we use really good representations of that speech audio, which we get with the work I discussed earlier, like with wave-to-back pre-training. And then we want to get meaningful units that we then can process individually. And we do this by doing a type of segmentation in a very, very simple way that I'll describe in a second. And once we have those units, then we can go about trying to learn to map speech segment units into phonemes. And we do this with adversarial learning, with generative adversarial networks. So to illustrate how it works is, we have a bunch of unlabeled speech audio in a particular language. We have a bunch of unlabeled text that can come from different sources. So we tried like Common Crawl, for example, like just web text, but also like other sources. And starting with the unlabeled speech audio, what we do is we first embed it. Well, we first learn speech representations, wave-to-back, and then we embed this unlabeled speech audio. So we get representations for wave-to-back to represent this speech audios. And then we want to go about segmenting those speech audios into smaller units. And we do that by a very, very simple method. But just doing k-means clustering of these speech representations. So I drew these little dots here under the unlabeled speech audios, which represent like these 25 millisecond CNN outputs, remember, that have like a stride of, I think, 10 milliseconds it is. And these are these little circles here. So maybe they should be actually squares, because this is what I used previously. But anyway, so we just do k-means clustering. I think we use 100 cluster centers. I can't remember, something like this. And then when we're done with the k-means clustering, we can write down for each one of those circles the cluster ID. And that's what we do for a particular sequence. We write down the cluster ID. And then as soon as the cluster ID changes in the sequence, we introduce a segment boundary. And then when we have that segment boundary, we just mean pool all of those representations that are not necessarily the same, right? They just have the same cluster ID, but they're not necessarily numerically the same. We just cluster them together, mean pool them together to get a vector for each segment. And this is what the different rectangles here denote in different colors. And that's what we feed into our generator. So maybe how, in a nutshell, how generative adversarial training works is that you have a generator that gives you an output, and that writes down maybe like a transcription, like in our case. Let's go through this. So we get a phoneme sequence here for this particular audio sequence, and this is a little neural network that just gives us that based on these segment representations. And then we have a discriminator that looks at that and tells us if this is a real output or if it's a fake output. And the important, the reason, the way this works is we feed into this discriminator sometimes output from the generator, but sometimes outputs, sometimes just unlabeled text. So sometimes we just feed real text in there. And the job of the discriminator is to tell us if this, if the input is actually unlabeled text or if it's output from the generator. And this is how we get training signal. So there's no supervision. The only thing the discriminator has to figure out if it's real or not. And then once the discriminator gets good at distinguishing that things are from the generator but not real text, then the generator hopefully gets better in producing more realistic looking phoneme sequences, and this way tries to fool the discriminator.
Michael?
Yes.
A couple of questions on this slide. So one, I think you mentioned this, but just to confirm, wave to vec output in this case is just continuous representations, right? Not the character level hypotheses of the transcriptions. You're clustering continuous representations in this case, right?
Yes, it's just a bunch of vectors. Yeah.
And can you comment a bit on the step 6, which is the phenomenize? So the unlabeled text is converted into a speech signal, or were you going to do that?
I will have a slide about that later. This is
Awesome.
just the overview. Yeah, actually, let me just go on and then describe those things. I will be done in a few slides, and then I can.
Yep, go ahead.
Okay, so the segmentation here, I talked about that. We basically just introduce a phoneme boundary as soon as the cluster ID changes, right? So what I'm showing here is like at the bottom some real speech audio actually, and then the third row is the goal segmentation. So this is something we have that a human annotated. And then we also have like the phoneme there for the utterance Jane may earn, and I think it's more money. And then the top two things are from our approach. So the k-means segmentation here is really just from this k-means ID, from these IDs that we get from k-means. And then what I denote here as GAN is after it actually, this is what the generator produces, because what the generator does is it can actually undo some of these boundaries through the use of some additional pooling, actually. So, but yeah, maybe I'm not going into this detail, but just to get a bit of a feel of how that works. So the point is, like, the GAN output afterward is actually pretty not too far away from what humans would annotate. Of course, it's not perfect, but you can produce fairly decent segments there. In terms of text data preprocessing, so this could be data from the web. What we do is, we have word boundaries there often, at least for English, and then we just use an off-the-shelf phonemizer. The phonemizer is a tool that turns these words into phonemes based on either a machine learning model or some annotations from humans. And then you get phonemes for these words. But what we also do is we also insert silence, because in the speech audio recordings, people don't have pauses when they speak, right? And so in order to be able to account for that, we also insert silences, even in the unlabeled text, just to make that unlabeled text look realistic. So there's definitely a silence at the beginning and the end of each utterance, and sometimes in between as well. How does the GAN training work in detail? So what the way we go about it is that on the left, the unphonemized text, we just turn it into one-hot vectors. So for each one of the phonemes that I just showed a second ago for the unlabeled text, we turn it into one hot vector, so that looks similar to the discriminator of what the generator will output, because what the generator outputs is a probability distribution over phonemes for each one of those segments. And what we also do is, like, sometimes the generator, these segments are not perfect, so there might be the same phoneme being predicted in the generator for two subsequent segments, and then we just combine them if the output is identical by just mean pooling them. And then we feed those representations into the discriminator. And what's interesting is that the model the training is actually not really, it doesn't really hurt that on one hand you have a probability distribution, and the side you have one hot vector. So in practice, it's not a big issue. The generator and the discriminator are actually very, very simple models, and that's something that is, I think, actually a very important detail. So they are really, really tiny. So the generator is just a single layer convolutional neural network with less than 100,000 parameters, and we keep the pre-trained representations frozen. The discriminator is also just a very simple 3-layer CNN, and this entire approach can train like on a single high-end GPU in like overnight, pretty much. And that's very nice. And we keep that on purpose simple, just because there's this adversarial game going on between the generator and the discriminator. So if one of them is just a really powerful network, then it's really easy to fool the other one, right? So if the generator is like some, let's say RNN or LSTM or some kind of transformer or something, then a discriminator, which is a simple CNN, will have a hard time to keep up with that. because they're always trying to outsmart each other. Maybe I stop here for questions.
We don't have any new questions that have come in, but I do want to comment for students that we will do a deep dive into GANs towards the last module in this class when we cover VAEs, generative models, and GANs together. Go ahead, Michael.
Right. Then let me just finish off here on this and then conclude. So typically, also one important detail is also that people use how do you know how do you know that your model works well, right? So you can just use labeled data for development, right? But then it's not unsupervised anymore. So we actually spend a lot of time on coming up with unsupervised metrics to do early stopping and hyperparameter selection. And I'm not going to go into detail, but in the paper about that. Another thing we do is we do the self-training again after the GAN training. So you do this. You estimate your unsupervised model, but then you can still go out and do semi-supervised learning again, and that worked pretty well in our case, as we'll show. You can always combine ideas here, so that's quite nice. How well does it work? It works pretty well compared to the previous best result in this area, which people haven't worked a whole lot on, just because it is very hard. There's a very significant error reduction compared to the previous approach, more than half then. But what is most interesting actually is how does this compare to supervised systems? So we get a bit of an idea, like, is this really something that is viable, right? Compared to if you would collect a lot of data, and the answer is that it's actually pretty good. So again, I'm showing here the graph of like the best systems over time. And of course, it's not as good as the best system that from very recently, but it's as good as some of the best models from just 2 years ago. And this uses no supervision whatsoever. So that's quite nice to see that we can build models of good quality there. Now, everything I spoke to about was again for English, right? And that's mostly because there we have like the best systems. But what about other languages? So here is a bunch of European languages, and what we can see is that compared to strong supervised systems, the approach is of course not as good, but it's still decent in many setups. And again, some of these models they use a lot of sorry, now I have to actually pause for a second. Sorry about that. It was my break reminder. So it performs pretty well. And what's even more interesting is for languages for which we truly don't have very much data. For European languages, we have a lot. But for some languages, like Asian language here, Tata and Kyrgyz, or African languages, we have very little training data. And again, like the unsupervised approach does maybe not as well as the best supervised systems, but it does pretty well. And we also realized we had a flaw in our experiment there. We used a lot less unlabeled data than we could have, but for another time. So that's very promising to see that we can now build speech recognition systems for languages that truly don't have very much data. Okay, that's pretty much it. In summary, this is a very lightweight approach to learn speech recognition models on top of wave-to-back, which is pretty bulky, but once you have the wave-to-back models, you can actually train these models very easily. And the wave-to-back model is publicly available. Why does it work? Well, good audio features are really the main reason why this approach does better compared to prior work. So that's the main reason. And one downside is that you still need the phonemizer, right? I said this is something that phonemizers sometimes are built. They use human annotations of what phoneme should be in a certain word. So that is still a downside. So that is an opportunity for future work to see if we can directly do unsupervised speech recognition with graphemes or letters. That would be really nice. And the segment construction we have is a very simple approach. So there's a lot of more approaches that are much better than that, but we didn't try that yet. So that's something that can definitely be improved. Cool. That's pretty much it. So pre-training for speech. is something that is now really competitive to semi-supervised methods, works much better in low resource setups than those, and is also competitive for high resource setups. Learning representation across languages works very well, helps low resource languages. And all of this can really help to build speech technology for languages where there's very little labeled and unlabeled data. And we hope that this will make speech technology much more ubiquitous and robust with more applications for more people in the world. And if you're interested, the code and the models are all available on our FAIRSEEK GitHub repo, as well as also Hugging Face. Thank you.
Thank you, Michael. I think I won't speak for the students, but I know I particularly appreciated this overview. It's always good to hear from people who are operating at the cutting edge of an area. One question that has come in, and you should answer this to the extent that you can. How are some of these models applied in production at Facebook or at other places?
That's a good question. So they're definitely finding so if you just look at the research papers that are out there, right? So there's research papers from the main companies that use speech recognition today, like Amazon, Google, Facebook, of course. And you can see that there's applications in all of these domains that I mentioned initially, like obviously speech recognition, speech translation. So yeah, so this is being used very widely, and I think people are seeing the opportunity there to really move away from or to make speech technology just much more ubiquitous, right? So previously the big companies, they were like, well, most of our customers, they speak English, they live in this region, and then there's maybe, I don't know, a few other languages, no more than like 20 or 30 or something like this. But I think this opens the door to really serve a lot more people who speak languages that there hasn't been so much investment in. Yeah.
Great. So I guess one last question that I see here is, can you comment on what we might expect in the next 3 to 5 year horizon? Like low resource languages seem to be the focus, and do you see the performance on, like, is the science fiction future of the Babelfish, where anybody can talk to anybody because there's a real-time translation device plugged into people's ears? How feasible is that future?
I think it's actually so there's products out there, right? So for example, the other day with the Pixel 6 release, I think it was, right? So they built some really cool, at Google, they built some really cool like speech-to-speech systems that work pretty well. Like there was a demo like for English to Japanese translation, which is really hard, right? Japanese is a very, very different language to English. Everything is a completely different order. It's actually pretty much reversed to English, right? And they had like a pretty cool demo there. So I think this is not too far away. I do think actually speech translation is actually super interesting because there's very little labeled data, right? You need data from some recording being translated, right? And there's many different directions. Let's say you have 100 languages you want to translate between. That's like nearly 10,000 directions, right? So the amount of label data will be very limited, right? And this is where these kind of sample efficient methods like self-supervised learning or semi-supervised learning, they can really shine. They can really make a difference because you just will never have enough data in all these directions. So I think there's a lot that can be done. And speech translation has been shown to benefit a lot from this type of work.
Got it. Okay, so I think we've asked you a lot of questions throughout the class. We're 5 minutes over the time anyway, so we'll let the students go and we'll let you go. Thank you again, Michael. I think we really appreciate you taking the time and telling us about this area.
Thanks for having me. Thank you very much.
Thanks.
And if you have any questions, feel free to get in touch. You can find my contact details online, so feel free to shoot me an email.
Perfect. Thank you.
Thank you. Bye.
Bye.